Hello everyone and welcome back. My name is Mr. Cobalt, and in this video we're going to go over how to use the rate law in order to calculate the time it takes for a certain amount of reactant to disappear or the half-life of the reaction. So let's get into this. Okay, so in this problem we have the reaction N plus M gives us the products O and P, and they give us the rate law, which is the rate is equal to 3.5 times 10 to the negative 3 per molar per seconds multiplied by the concentration of N squared. If the initial concentration of N is 0.8 molar, how many minutes passes before 65% of N has reacted? And what is the half-life in seconds if the initial concentration of M and N are 1.3 molar and 0.6 molar respectively? Okay, so let's start with the first part, which is what is the amount of minutes or how many minutes will pass for 65% of N to react. First thing we need to know is what is the rate law, or I'm sorry, what is um, the order of this reaction. And so they gave us the rate law here, and we could see that the only substance that is in the rate law is N. So that's the only substance that's going to affect the rate of the reaction. And we can see that it has a superscript of 2. So that means that this is an second order rate law. So that means it's second order with respect to the concentration of N. So we're going to have to use the integrated rate law with respect to the second order. Okay, so remember there's 3 orders. There's 0 order, there's first order, and there's second order. And each of those has a different integrated rate law. So we got to make sure we're using the right integrated rate law for the right reaction, right? So we have to use the integrated rate law because the integrated rate law has time involved and they're asking us about time. So we're going to have to use the integrated rate law. So what is the integrated rate law for a second order reaction? That's going to be 1 over the concentration of some substance A and over time. So over a certain amount of time. And that's going to be equal to the rate law constant multiplied by T time plus 1 over the initial concentration of this substance we are looking at. So this is the generic equation. A is just whatever substance we're looking at. So since we're looking at the reaction with respect to N, N is the reactant here in our equation. So we can rewrite this as 1 over the concentration of N at time t is equal to the rate constant times the time t plus 1 over the initial concentration of N. So there's the equation. This is our integrated rate law. So now all we need to do is plug in the information that we know. So we're looking for the time. So we want to find how much time does it take for 65% of their reactant to react, to disappear. So they gave us here, where is it? 0.8 molar for the initial concentration. So N, the concentration of N, the initial concentration of N is 0.8 molar. What about the concentration of N at time t? How do we find that? Well, let's set up the percentage. One of the things we got to remember is that a percentage is a part divided by a whole multiplied by 100. So that's the generic equation for percentage. So if I write that down, let's write it over here. So a percentage is equal to a part divided by the whole times 100. Okay, so if you're ever confused about like how do I figure out what the amount is at time t if they just give me the percentage, well, use the equation for a percentage. So in this case, the percentage that we're given is 65% that has reacted. So what we have to remember is in our equation here, this is the amount that's left over after a certain amount of time. This is not the amount reacted. They're giving us here the percentage of the amount that has reacted, which means that if 65% reacted, that means 35% is left. So 35% is left would be this here, this concentration of N at time t. So we can set up our equation using 35%. So 35% is left over. Well, that's going to be equal to the part over the whole. Well, the whole is the total concentration that we had started with, right? And that is 0.8 molar. So that's the total concentration we started with. And then after a certain amount of time t, we're left with only 35%. So that whatever that is, that's going to be the concentration at time t. So the concentration of time t is what's left after that time, after 65% has reacted. And then, of course, this is multiplied by 100. So all we have to do is solve for the concentration of N at time t. So to do that, we are multiplying by 100. So we want to divide both sides by 100, like so. So that cancels out. And then 35 divided by 100 is going to be 0.35. And of course, that's going to be equal to the concentration of N at time t divided by 0.8 molar. Here, let me write this lower so it's out of the way. So this is going to be 0.35 is equal to the concentration of N at time t over 0.8 molar. So now all we need to do is multiply both sides by 0.8 molar to get the NT by itself. So we're going to multiply by 0.8 molar, multiply on this side 0.8 molar. So this cancels out. And then so 0.8 molar times 0.35 gives us the concentration of N after time t. So when we multiply these together, we get the concentration of N at time t is equal to 0.28 molar. So that is the concentration of N at time t. So now we have that. So that's 0.28 molar. So now we can take this and we can take this number here, this number is K. Remember? So the rate law is the rate equals K times the concentrations of the substances that are affecting the rate raised to their respective powers. So this number here has to be K. So we can plug that in. So we can have 1 over NT. So NT is 0.28 molar. So we'll go ahead and substitute in. So this will be 1 over 0.28 molar is equal to K. So that's going to be 3.5 times 10 to the negative 3 per molar per second, multiplied by T, plus 1 over the initial concentration. So that was 0.8. So it's going to be 1 over 0.8 molar. So I just plugged everything in here. And so now all we have to do is solve for T. So I'm going to subtract 1 over 0.8 molar on both sides. And when I subtract those two, I get 2.3124. So I get 2.3214 molar. Oh, not molar, sorry. Well, molar per molar. So notice that molarity is on the bottom. So it's 1 over molarity, which is the same as molarity to the negative 1. So just to review really quick. So remember, if you have 1 over something, 1 over x, that's the same as x to the negative 1. So there's a power of 1 there. Or if you have 1 over x squared, that's the same as x to the negative 2. Or if you've got 1 over x to the third, that's the same as x to the negative 3. So basically, if you want to bring your variable from the bottom to the top, you have to change the sign of the exponent. So this goes from a positive 1 to the negative 1, positive 1 to the positive 2 to the negative 2, positive 3 to the negative 3, and so on. So I'm doing the same here. So since the unit here is on the bottom, it's molarity, 1 over molarity here. So since I'm subtracting, my unit would be 1 over molarity, but 1 over molarity is the same as molarity to the negative 1 power. So we say per molar, right? Because it's on the bottom, 1 per molar. Okay, so I have 2.3214 per molar here. That's going to be equal to 3.5 times 10. Oops, let me make that better. 5 times 10 to the negative 3 per molar per second times T. So now I just divide both sides by the K. So divide both sides by 3.5 times 10 to the negative 3 per molar per second. Divide this side by 3.5 times 10 to the negative 3 per molar per second. So this cancels out, leaving me with T. So when I divide these, I'm going to get T is equal to something. Now, before I divide them, notice I have molarity to the negative 1 here, and I have molarity to the negative 1 here on top and bottom. So that's going to cancel out. So those will cancel out, leaving me with per seconds on the bottom. So, but remember, if I bring it on the bottom to the top, I have to change the sign. So bringing it to the sign would be seconds. So I'm going to get time in seconds here. So when I divide this, I get 663.26 seconds. But keep in mind that they want minutes here. So they're asking for how many minutes pass. So I'm going to have to convert this to minutes. So I take 663.26 seconds over 1. I'm going to use my conversion factor that 1 minute is equal to 60 seconds. So I put 60 seconds on the bottom, 1 minute on top. Seconds cancel out, and I get 11.1 minutes. So that is the amount of time that it takes for 65% of the concentration of N to react. Okay, so now that's the first question. What about the second question? What is the half-life in seconds if the initial concentration of M and N are 1.3 molar and 0.6 molar respectively? Well, if we go back to our rate law here, you'll notice that the only substance that we have the concentration of in our rate law is N. And what does that mean? It means that N is the only substance that affects the rate. M doesn't affect the rate. So changing the concentration of M does not affect the rate of the reaction. So we can ignore that. So we can focus only on N. Second thing is, remember, just like we had to make sure we use the right integrated rate law that fits or corresponds with the correct order of the reaction, we have to do the same thing for the half-life equation. So each ordered reaction has a certain equation for the half-life. So we need to make sure we use the correct half-life equation. So let's go ahead and do that. Let's erase this. We don't need this anymore. So we had the time 11.1 minutes. Now for the half-life equation, since we have a second order with respect to N, then we are using second order half-life reaction equation. Okay, so T 1/2, that's the half-life, that's going to be equal to 1 over the rate constant multiplied by the initial concentration of N. So all we need to do to figure out the half-life is plug in K and plug in the concentration of N that they gave us. And so let's go ahead and do that. So K is the same as before, 3.5 times 10 to the negative 3 per molar per seconds. 3.5 times 10 to the negative 3 per molar per seconds. And we're going to multiply that by the concentration they give us. So concentration of M is 1.3. We don't care because M doesn't affect the rate of the reaction because it's not in the rate law. So the concentration of N is 0.65. So we're going to put that in 0.6 molar, sorry. 0.6 molar. And then all we need to do is calculate that. And when we do that, we get 476 seconds. 476 seconds. So that, ladies and gentlemen, is the half-life for this particular reaction. So again, remember, one of the keys to solving these type of problems is, one, identify the rate law order. What's the order of the reaction, and figure out what equations, what integrated rate law equations and what half-life equation you need to use that corresponds with that order of the reaction. I hope this was helpful. If this helped you in any way, if you enjoyed the video, then please by all means like the video, share the video, hit that like button. Also, make sure that you subscribe to my channel, help me out. Hit that notification bell up there somewhere. Also, when you do that, make sure you click all so you can be notified by all the videos I put out. And finally, put a comment down below in the comment section. Let me know what you think. Ask me questions. I would love to hear from you. If you have a question or a problem you need help with or a topic you would like me to cover, let me know. I want to do that for you. Thanks for joining me and have a great day.